Previously, we took a look at the motion of a single charge in an electric field. And now I would like to imagine what would happen if I had a dipole sitting in an electric field. So remember, a dipole is a positive and a negative charge that have been separated by some distance. And usually they're somehow physically held together, like say they're two ends of a polar molecule or something like that. So we'll imagine that that's the case here. So I've already drawn in the dipole moment. Remember, the dipole moment points from the negative charge towards the positive charge. Now, it doesn't actually matter that I drew it connecting the two charges, and that's because it's not the same physical quantity as the disk separation between the dipole, the two charges in the dipole, which I noted with S. So what I would like you to do is try to convince yourself that if the dipole is free to rotate, it's always going to attempt to align itself with the external electric field. So pause on that, and then we'll get back and work on that. Okay, so let's go ahead and actually figure out the torque on our electric field. So to that end, let's figure out the electric forces. The positive charge is going to feel a force F pulling it up, and the negative charge is going to feel a force F pulling it down, and these are equal forces in magnitude. So this means that the force will add up to 0, so there won't be any motion of the dipole up or down if the dipole is initially at rest. That doesn't mean, however, that there isn't a torque happening here. So let's go ahead and start figuring out what that torque would be equal to. So each force is going to contribute a torque. And so here I'm just drawing the lines of action of the force. And remember, the lever arm right here are perpendicular, is the shortest distance from the rotation axis to the line of action. So, well, this distance is s over 2. And then this angle here is this angle here. That's going to make it a sine. So it's s over 2 sine phi. So then my total torque is going to be 2 times r perp F. So this will be equal to 2. My r perp is s over 2 sine phi, and my F is QE. Okay, so the 2's cancel, and I am left with QSE sine phi, and I put the Q and the S together because we remember that that's the dipole moment, so PE sine phi. So if we're working in magnitude, that would be enough, but we can go ahead and actually try doing this as vectors. So if you see two magnitudes and a sine of an angle, what kind of vector operation are you suspecting here? Yeah, that's right. It should be a cross product. So we're hoping that we can write it as tau equals P cross E. The other possibility would be that it's E cross P. So you can do this with the right-hand rule to convince yourself that it's going to work out. And I'm really sorry I'm going to be drawing the world's worst right hand. So if you remember, you take your right hand and you point your index finger along the first line that you want to take a cross product with. So in that case, that'll be P. And then your middle finger will be hanging out. And you're free to move this one back and forth to get a nice, good fit. So we'll go ahead and align it nicer with the electric field, like so. So sure enough, that's the second line. So then the cross product itself would sit out on your thumb, and I'm just going to label that as your thumb. I'm really sorry. of your right hand. And so if you do that exercise, if you do P cross E, you get that the torque winds up pointing out of the screen. So that makes sense because you remember out of the screen corresponds with a counterclockwise rotation. All right, so you can also just double check it by saying, what if P pointed the other way and this was E, right? In that case, the torque would be into the screen, which would correspond to a clockwise rotation. So this is indeed the correct form. And what we get is that the dipole will always try to align itself with the electric field. And the torque will be the greatest when the dipole moment and the electric field are at right angles. And it'll be at 0 when it's aligned or anti-aligned. Now, if it's anti-aligned, this would correspond to a position of unstable equilibrium, because if you so much as look at it funny, you'll displace it out and then it will twist around to align with the electric field. In sides, as a practical matter, you can never align anything perfectly anyway, or anti-align. So just as kind of a follow-up thought here, imagine you take your dipole and you place it down angled to the electric field and then you let it go. What kind of motion is it undergoing? Okay, well, since the torque is always a restoring torque, it's always trying to turn it towards the aligned position, it means it's harmonic motion. Now, because it depends, it's the sine of the angle rather than the angle itself, it's not simple harmonic motion, although you can approximate it as that if the angles are really small. So let's just, for real quick, to get some sense of the numbers, I drew this dipole at about a 30-degree angle. So let's go ahead and say that our charge was a nanocoulomb. And let's make the separation, say, a micron, just to get something on a molecular scale. So a micron is about 10 to the negative 6 meters. And let's say we stuck it in 1,000 Newton per Coulomb field at 30 degrees. Well, we can get the direction by the right-hand rule, which we already did. So the magnitude is just going to be PE sine phi. So that's QSE sine phi. So my charge is a nanocoulomb is 1 times 10 to the negative 9 meters. My distance is 1 times 10 to the negative 6 meters. For an electric field strength of 1,000 newtons per coulomb, and then I need a sine 30. All right, sorry, 10 to the negative 9 coulombs, of course. All right, so let's check this out. Coulombs cancel coulombs. I'm left with Newton meters, which are indeed units of torque. And this is going to be 5 times 10 to the negative 13 Newton meters, because the sine of 30 is a half. Now that doesn't seem like a whole heck of a lot of torque, but keep in mind if you're talking an object like a water molecule or something like that, it doesn't have a very large moment of inertia either. So you actually get pretty decent angular accelerations. All right. And to kind of close this out, something that I also want you to do is think, if you have a dipole that just happens to be hanging near a point charge, positive or negative, doesn't matter, so we'll do them both. And there we go. We'll just draw a big line there. if I were to stick a dipole over here somewhere, and it's free to rotate, I want you to convince yourself that it will ultimately be attracted towards the charge, regardless of the initial orientation of the dipole, and also regardless of whether the point charge is plus or minus. So pause the video and then we'll get back to it. All right, so let's go ahead and draw some electric fields here. So first off, I think you should have been able to convince yourself that if I go and place a dipole, let's say here, it will eventually rotate to align its dipole moment with the electric field. That part still works. Well, then that effectively makes this a positive charge and that a negative charge. But now, unlike the case we looked at before, the electric field strength here is greater than it is there, because here the lines are closer together and here they're further apart. So this means that the electric force that the negative charge feels is greater than the repulsive electric force that the positive charge feels, and so we end up getting a net force towards our positive charge. And if this were a negative source point charge sitting over here, and I do the same thing, again, it's going to be exactly the same deal. The dipole will go ahead and rotate so that the dipole moment is aligned with the electric field, like so. And again, looking over here, the electric field strength here will be greater than the electric field strength there. So again, if we draw a free body diagram for this, the force that the positive charge feels will be greater than the force that the negative charge feels. So the net force will again be towards the negative charge. Alrighty, in the next few videos, we will be taking a look at Gauss's law. Have a good one.